And now we will do macro charge. Macro just meaning large. So in physics, we often talk about a body. So we don't really mean anything specific by body. Body just means a large object made out of matter. That's pretty much all it means. In electrostatics, one of the greatest things to use as a body is Teflon. Teflon has very useful properties, which we'll be showing you very soon. So when I first taught this class, I went back into the demo closet and said, well, I need the Teflon rod to do all the demos. And I was extremely disappointed. This big, beautiful lecture hall with 280 seats and full of students eager to learn about physics. And this is the Teflon rod in Physics 102 at Rice University. This is what I was given to demonstrate electrostatics. I couldn't live without it. So I got in the McMaster catalog and I bought this. This is a Teflon rod. You can really do demos with this. You can really go to town and explain some physics with this Teflon rod. So we will be using this Teflon rod quite a bit in our demonstrations and in our explanations of physics. So our body is simply a Teflon rod, and it weighs 0.37 kilograms. So what's the first thing we want to do? Well, I guess if we want to think about charge in this rod, we simply say how much charge does it have? And you can actually figure that out from what you already know from the micro scale of charge. Because you could say, okay, this thing weighs 0.37 kilograms. And we learned that the mass of charge was very small, 1.7 times 10 to the minus 27 kilograms per nucleon. Where a nucleon is either a proton or a neutron. Just if you're talking about one or the other, you call it a nucleon, things that live in the nucleus. So we have our big mass divided by the mass of an individual nucleon, and you put those together and you get 2.2 times 10 to the 26 nucleons. So you actually don't need to know the chemistry of this thing or even what atoms are in it. If we know that it weighs 0.37 kilograms, we know that that mass is almost all in the protons and neutrons. The electrons don't weigh much. Then we can actually estimate the number of nucleons in this thing. Now, another thing we need to know about atoms is that there's usually roughly equal numbers of of protons and neutrons in the nucleus. It's almost never exactly equal, but it's usually very close. With lithium, it was 3 and 4, and it's usually closer than that. So if that's true, then we know that roughly half of the nucleons are protons. So we know we have 1.1 times 10 to the 26 protons. Okay? And if that's true, now we can figure out the charge because each one has a charge of 1.6 times 10 to the minus 19 coulombs per proton. Okay? So if you multiply those two, you end up with 18 times 10 to the 6 coulombs. That's 18 million coulombs. There are 18 million coulombs of positive charge in this macroscopic Teflon rod. Now, if I were really holding 18 millions of coulombs of charge, it would be the greatest demonstration you've ever seen in your life. It would blow you away. I mean, it would literally blow us all away. Out of the room, building would be gone. Okay? But we survived this demo. We aren't all, well, I guess only I and the cameraman would be blown away because this is a distance thing. But we survive because there's not just 18 million coulombs of positive charge. There's also 18 million coulombs of negative charge. This is the difference between microscopic and macroscopic. So in addition to all the protons, there's electrons, and they're so mixed together so tightly that we don't see the charge in the macroscopic world. So it does have 18 million coulombs of protons, and it does have 18 million coulombs of electrons. But when you put them together, you get something that macroscopically just appears neutral. And this is how you have to keep in mind about macroscopic objects. When we say they're neutral, they're actually still fairly exciting. There's still a lot of charge in there. It's just completely mixed together and balanced.